In this lecture, we will calculate an effect size index and interpret it, and we will compile descriptive statistics and an explanation of those statistics into a descriptive statistics report. Statistical analyses usually involve some sort of conclusion about how similar or different two or more groups of scores are. However, one of the pitfalls of statistics is that the math itself can be misleading. For example, there's a thing called statistical significance that we'll discuss later in this course. Statistical significance is something that is declared after analyzing numbers, usually to see if groups of numbers are different enough from each other to be considered actually different, and not simply different due to chance alone. Regardless, this declaration of statistical significance can be dangerous, especially to the layperson, or to the lazy person who doesn't take the time to see how the study was designed. Because a researcher can achieve statistical significance simply by manipulating a design or by having a large N. So, back to the point of this lecture. One of the strategies we use to help understand whether a finding of statistical significance is meaningful is by calculating something called the effect size index. I like to consider effect sizes as measures of meaningful significance. The larger an effect size index, the more different the two populations in question are. Take a look at figure 5.4. There are three scenarios. On the top is a scenario in which two populations, A and B, are compared. The populations are very similar in terms of their means, ranges, and other descriptive statistics. Notice how they essentially overlap one another? You could perceive this overlap as meaning a score randomly chosen from one distribution may have looked like it belonged to either distribution, because both are so similar in the way their scores are grouped. The effect size for this example is very small, calculated at D equals 0.20. Look at the equation used to calculate the effect size index. The index is a way to look at the difference between two distributions' means in terms of their combined standard deviation. In a way, it's kind of like a z-score because the answer is expressed in standard deviation units. For example, a D of 0.5 means the two populations' means are separated by 1/2 of a standard deviation. Look at the middle example in figure 5.4. Notice how the box plots are shifted. Now look at the frequency polygons. The mean of each distribution is at the center, from the topmost part of the bell curve. Follow this point down to the horizontal axis, and you can mark the mean. If you do the same for the second distribution, you can see that the distance between these two means, expressed in the standard deviation unit, is D. These distributions yield an effect size of 0.5. These distributions have what Cohen termed a medium effect, meaning the distributions are different from each other, but not dramatically so. Finally, the bottom example in figure 5.4 shows two distributions with a large effect size, indicating that they are quite different from each other. Notice, however, there is still a great deal of overlap between the two populations. However, there are now unshared regions where a score from, say, the left region, specific to distribution A, is very unlikely to be also found in distribution B's scores. Let's calculate some effect size indices. In problem 5.11 from your text, you're given three scenarios where you are told what the group means for two different groups and the overall standard deviation. And we've been asked to not only calculate the effect size index, but also interpret what that index means. So for effect size calculations, it looks like D, which is the symbol for effect size, is equal to the difference between the population parameters of the mean over the standard deviation. Now, for the population parameters for the means, what we're going to do is we're going to use the sample means to estimate the population means. It's a very common statistical technique. The standard deviation thing is a little bit more complex, and like Spatz says, we'll deal with that later in the course. So for right now, you just have to trust us that the standard deviation given is the one that's appropriate for this calculation. So let's start off with part A. In part A, I have a group 1 mean of 14, so I'm going to assign that mu1 equals 14. And a group 2 mean, mu2, of 12. And a given standard deviation of 4. So to calculate my effect size index, I'm going to subtract the means. So mu1 minus mu2, and divide it by the standard deviation. Okay, that gives me a pretty easy math problem telling me the effect size index is 0.5. Now, according to the somewhat arbitrary but widely accepted limits, Cohen's limits for these, 0.5 represents what we would call a medium or moderate effect size. Now, what does that mean? Well, let's assume, just for the sake of this drawing, that both the populations for group 1 and group 2 are normally distributed. So I'm going to draw what it would look like if you were to plot them on the same horizontal and vertical axes. There's one of them. There's the other one. Now, I've tried to make it obvious, but you can see that the blue distribution has a higher mean, I meant that to be purple, than the purple distribution. And on a number line, it would be conceivable, depending on the scale, of course, for the blue distribution to have had a mean of 14 and the purple a mean of 12, which would make the blue distribution the population for from which group 1 was chosen, and the purple from which group 2 was chosen. Okay, so all this really says is that the populations are different. And they're different in that their means are split from each other, and they're split by approximately a half a standard deviation of the standard deviation of the two of them put together. Now, that is called a medium effect size because it is a pretty decent difference. It certainly isn't anything like wild where one of them ends up all the way over to the right or to the left, but it's better than if we had, say, laid them right on top of each other. So remember, effect size is supposed to give you some sort of a feeling for just how different the differences are. And in this case, we would call it a somewhat moderate difference in which population 1 was greater than population 2. Let's go ahead and do the next sample, problem B. In problem B, it looks like group 2 is quite a bit larger than group 1 on first glance. But be careful. Look at that standard deviation as well, because it moderates what that difference of 10 and 19 appears as. So let's go ahead and do the math. I know that my effect size is represented by the symbol D, and it's mu1, which in this case is 10, minus mu2, which is 19, taken from right there, divided by the standard deviation of 10. So the D for this is going to be negative 9 over 10, or negative 0.9. Alright, now don't freak out over that negative. All it means is that population 1 this time was less than population 2. Okay, but in terms of the interpretation, we're still concentrating on just the quantity of this number here. And we would call that a large effect size. In fact, it's almost a full standard deviation different. So if I were to draw these guys, if I had one of them here, And then the second one, I'll choose a different color, needs to be almost a full standard deviation, so it should peak right about there. And we'll learn more about how to gauge where those standard deviations are as we move into normal distributions here in a little bit. But for now, it's pretty obvious that green is greater than red. Green representing, in this case, then group 2 with a mean of 19, and red representing group 1 with a mean of 10. So now we can see that these two populations have been split farther from each other than our previous example, meaning they're more different. That's why the effect size is termed large, because they're so different they're almost a full standard deviation away from each other. All right, and C. Same values, 10 and 19. Oh, I see why Spatz is doing this. Because what did he change? He changed the standard deviation. Because remember before, in B, we called that effect size 0.9 or negative 0.9 large. Now we're going to work with the same means, but because the standard deviation is different, it's going to give us a very different interpretation of the effect size. So the D in this case will be equal to 10 minus 19, so that looks familiar. But now we're going to divide by 30. So that gives you negative 9 over 30. And if I type that into a calculator, I get negative 0.3. Now, again, the negative simply tells me that the first number, which was the population for group 1, representing group 1, was smaller than the other. But now this 0.3 is a smallish effect size difference. So let me try and represent that graphically. And so if here we go, I'm going to put the number line in first this time. It's going to give me a little bit of a grounding. If that is going to be the group 1 mean of 10, then that's about where the first standard deviation is. If that's 30, then that guy would be 40, which means my group 2 mean of 19, I'm going to change colors, 10, 20, 30, 40, so 19 would be right around here. So I'm going to make a dot where I want the top of my curve to sit. Okay. Now hopefully in this one you can see that yes, the blue distribution has a higher mean than the red distribution, but there's an awful lot of overlap. This entire region in here of the overlap, those are basically participants in both groups that you can't tell apart. They are similar because they fit inside their distributions that they share. So think about it as the more different they are, the bigger these outside pieces will get, because there'll be more people that can't be confused with the other group. Because everybody in the middle here, in theory, you could take one person here and it could be that he's part of group 1 or part of group 2. You wouldn't be immediately able to tell just by looking at it. However, if you found somebody down here, you would say, oh gosh, that person's most likely part of group 1 versus someone on characteristics on the far right, part of group 2, where they don't share characteristics.
The last objective in Chapter 5 is to compile statistics and an explanation of those statistics into what Spatz terms a descriptive statistics report. In research papers, this section is essential to understanding not only the participants with whom you worked, but also your findings from the study. Spatz recommends beginning with a table listing the mean, median, minimum, maximum, 25th percentile score, 75th percentile score, and the effect size index for the two groups you are comparing. Then, you need to use this information to construct a box plot of the scores. Finally, write a brief narrative description highlighting the essential features of each distribution and stating the empirical conclusions. This section, however, is not for your discussion or interpretation of why such results are seen. Instead, you're simply stating a list of facts about how the numbers compare. Let's try an example. Anthony had students read a description of an assault and rape of a woman in a parking lot one night at 11:15 p.m. For some of the students, the woman was described as a nurse. For others, she was described as a prostitute. The students judged the amount of responsibility of the victim on a scale of 1 to 5, with 1 being no responsibility, and 5 being entirely responsible. Analyze their responses and write a descriptive statistics report. Let sigma equal 1. I made a summary table and box plot using Excel. You can watch the full 12-minute video at bit.ly/mazboxplots. I present the full findings on our next slide. To write the narrative for my report, I closely followed the structure Spatz used in Table 5.3. The graph shows box plots of the responsibility scores assigned by students when read a description of an assault and rape of a woman in a parking lot one night at 11:15 p.m. For some of the students, the woman was described as a nurse. For others, she was described as a prostitute. The students judged the amount of responsibility of the victim on a scale of 1 to 5, with 1 being no responsibility and 5 being entirely responsible. The mean responsibility score for the nurse description is 1.9. The median is 2. The mean responsibility score for the prostitute description is 1.8. The median is also 2. The nurses were rated on average 0.1 points higher than the prostitutes. While the two distributions have similar minimums and second quartiles, there is more overall variability in the prostitutes' scores. Also, both distributions have long tails on the positive side, yet their means are slightly below the medians. The difference in the two distributions is reflected by an effect size index of 0.1, which is considered very small. Thus, the data suggests that while the prostitute scores are more variable, the distributions are very similar.